Great. So yeah, let's kick things off. Welcome everybody. This is the third, I think, the third Sinter quarterly online meeting. So we started these back earlier in 2020, and it's a nice way for the international snow community to touch base regularly on and update each other on what's happening. We have interesting agenda today, 4 different things. We'll get right into the first presentation now. It's a science talk by César Deschamps-Berger. And he is just about completing his PhD now, focused on mountain snow. Before this, he worked both in France and in Norway, has a master's in geoscience, focused on tidewater glacier mass balance. So now he's turned his attention to seasonal snow. So César, we'll turn it over to you. You have about 25 minutes or so to present, and then we'll leave some time for questions and discussion at the end. So thanks for your willingness to present today, and you can take it away.
Cool, thanks. Now you should see my screen, isn't it? Can you see my screen? Yes?
Yep, that's great. You're good to go.
Yeah, okay, cool. Thank you. Yeah, wait, I just want to put a timer, otherwise I don't know how long I last. Yes, let's go. Sorry. So yes, I'm César. I'm really happy to present my PhD work to you today. I did it in Toulouse, in CEDIO, and in Grenoble, in the Center of Snow Study. And I was supervised by Simon Gascoin, Marie Dumont, and Etienne Berthier. And so I focused on observing and modeling the spatial variability of the snowpack in mountainous terrain. And that's what I'm going to present today. Spatial variability matters, especially if you're interested in hydrology and you want to predict the runoff of a mountain catchment, for example. Since with the same amount of snow distributed in different way, will result in very different runoff timing and intensity, as you can see on this figure from Freudiger. And that brings back to the general challenge of estimating the SWI, the snow mass, in mountains. And one of the best way, oh no, not best way, one of the most direct way to take into account spatial variability in SWI estimation is to combine high resolution snow depth maps with modeling. Since you will get the spatial variability from the snow depth map, and the modeling will provide the density, which you need to calculate the SWI, and as well a longer time period of study and different more variables. So I listed here a few studies which use this approach of combining snow depth, high resolution snow depth measurements and snowpack modeling. You can see that there's many different ways to measure, to map snow depth. And they differ by the accuracy with which they can measure the snow depth, and as well by the area that they can cover. So you have quite high accuracy, a few centimeters uncertainty with terrestrial laser scan, but you can only cover a few square kilometers, and you'll get much larger area with the airborne method at the cost of a slightly worse accuracy on the measurements. And you have as well many different ways to combine these measurements with the model. One which is often used is direct insertion, since you just take the snow depth you measured and you put it in the model, replacing whatever snow depth was modeled. It's fairly simple to implement, but it relies on strong assumption, which is that the observation is perfect. And so there are other ways to combine measurements and modeling. Particle batch smoother is a more complex one, in which you take into account the error from the model and from the measurement, but it doesn't allow to do prediction. It's only a reanalysis at the end of the melt season here. So the method we followed was to use satellite photogrammetry, which was used in such approach by Thomas Shaw in Chile once already. And it's a good method it's a good compromise between accuracy of the measurement and the area which is covered, which is of the order of hundreds of square kilometers. But direct insertion, again, is a bit limited because you make strong assumptions. So we would like to bring that a bit further. To do that, to use more complex assimilation method, you need a good knowledge of the error of your measurement. So that was the first part of this work that I'm going to present. It's what is the error of the snow depth maps? And then we try to assimilate it in a snowpack model and see what comes out of it. So the plan of my presentation, I'll quickly present how we calculate the snow depth maps, then how we evaluated them with some ASO product. And then I'll present the time series of 7 snow depth maps, which we use to assimilate in a snow depth model. So that's our workflow. You start on the top left with some stereo images, which are several images taken of the ground during the same flight of the satellite. And you combine them to obtain a digital elevation model, the topography. And doing that in summer and in winter, taking the difference, you'll get where there is snow, the snow elevation, the snow depth. One advantage of this product is as well that you get some multispectral images, which are easier to classify, and you can get as well quite accurate information about the nature of the surface, the nature of the ground. So make the difference between forest area, snow-free terrain, snow-covered lake, and so on. So we obtain what we want, which is a snow depth maps. Here at a resolution of 3 meters, but that's up to you to choose that, knowing that the original image resolution is half a meter. So how did we evaluate that? We planned an acquisition of the Pleiad satellite over the Tuolumne Basin in California, where the ASO is leading open flight. And by luck, that happened in the winter where there was lots of snow there. And by luck again, that happened just 1 day before an ASO flight, which is just pure luck, but we were happy with that. And since there's only a 1 day difference between the two acquisition, we can consider the snowpack didn't change much within this day, and then we can compare it directly. How it looks when we look at the map reproduced. On the left, you have the map produced with Pleiad images only, so that's a satellite-based product. And in the middle is the ASO product, and on the right is the land surface occupation map. So you can see that with this scale, which is quite large, it goes from 0 meters to 10 meters of snow thickness. It looks quite similar. And again, with the Pleiad product, you can identify some avalanche deposition or wind drift with on different side of a ridge. So that seems satisfying. Again, you can draw some profiles, and you'll see that with Pleiad in red, it's matching quite well what the ASO is seeing with airborne LiDAR, although there is quite more noise on the Pleiad measurements. That's another way to look at it, which is quite interesting for hydrologists when they want to know where there is snow, which means where there is water in the mountain. You draw snow depth aggregated per elevation, and you see that again it's matching quite well. Same with the general histogram, which takes all of the pixels snow covered of the area. And the mean snow depth that we recover is quite close to what the ASO is seeing as well. When you look at a pixel scale, so just a 3 meters pixel scale, there is still there is an uncertainty, which we measure here with the NMAD, which is the dispersion, but measured with a more robust way than the standard deviation. And this NMAD is around 70 centimeters. And there's as well a residual bias that we cannot completely take away, and which is here around 10 centimeters, but we expect it to be larger, and it was found to be sometimes larger, like 15, 20 centimeters in other studies. So that gives us a good idea of how is the error behaving in our maps. So the conclusion from that we take is that, again, the standard error is around 70 centimeters for the highest resolution we produced, 3 meters pixel. What I didn't show is that this error is decreasing when you take a larger averaging area, so 50 meters pixels and higher. And then the error is closer to 0.3 meters. And then there are some more things we did and that you can find in this article on the cryosphere. And I won't go into too much detail, but we try to find out what parameters are impacting the accuracy of the snow depth maps, such as the image geometry and other processing of the images. So now that we know how accurate our images or our products, we can try to apply this method. And here there's a nice time series of acquisition which were acquired between 2015 and 2020. We mostly have one acquisition per winter, kind of close to peak SWI. And yeah, so that's 7 days, except for 1 year where we have 2 acquisitions. So that's a small catchment in the French Pyrenees. Yeah, you have the forest at low elevation, and then it's just bare ground higher up. So that's the maps we get from this time series. So you can see that we have some problems sometimes with image saturation. These are the purple area on the maps, which means that you won't get, you're not able to retrieve snow depth. You're not able to retrieve elevation, so no snow depth. And sometimes we as well have some cloud occlusion. So these are typical limits of the photogrammetry method, which works with optical images. But you can still do a lot of things with the area which are observed. So one thing we did, thinking of Pablo Mendoza works and presentation last meeting, we drew some semi-variogram which are still interpreting. So for each date, one color is a date, and that's just the 2 semi-variogram for different range of distances. And what we interpret for now is that we find mostly the same break scale between 20 and 40 meters just by hand picking. And that's the magical number, which is always found with semi-variogram over snow depth. So we are quite happy. And there seems to be some difference with the total variance, which is much higher for the 2018, the May 2018 acquisition, which is as well the one with the latest in the melt season. So this might be related. We are still looking into that. If we go back to more hydrological applications, we try to draw the characteristic of the snow accumulation in this catchment. So on the left, you have the mean snow depth gradient along elevation for all years. Again, the same color for the same years. In the middle, it's the snow-covered area per elevation. And then when you combine both, you get the volume, the snow volume per elevation. And then we're able to see a bit where is the variability and where is the snowpack buildup in this catchment. And what we see is that there is some snow depth variability at all elevation, a bit more at high elevation. And there is snow-covered area mostly at low elevation, variability, sorry, mostly at low elevation. And then it results in a quite large variability of snow volume at all elevation, depending from one year to another. But we can see that all elevation above 1,600 meters are contributing. And this time, if we aggregate these metrics over the whole basin, so then you get the mean snow depth of the catchment here, the snow-covered area of the catchment, and then again, multiplying both, you get the total snow volume. And here we see that the variability, the interannual variability of the snow volume is mostly driven by the variability in the snow-covered area. And so we end up interpreting things about the interannual variability. And one interesting thing as well is the 2018 winter, in which we have 2 acquisitions, one in February in purple and one in May in green. And you can here even see the decay or the melt of the snowpack within one season, one winter, which means that we could aim at a higher frequency acquisition to have higher frequency time series. But with that, we only get the snow volume, and what we want again is the SWI. So we use this time series of snow depth maps in combination with the Crocus model. And so that's the workflow we used. I'm going to guide you through it so that's a bit clearer. So we generated ensemble simulations by, so these are gridded simulation distributed over the catchment at 250 meters resolution. And the simulation, the ensemble of simulations were obtained in 2 ways. One way by perturbating the weather forcings. So with random perturbation mostly, but as well, we applied some scaling factor to the precipitation. Because here, as input, we used the saffron forcing, weather forcing, which are available only over the French territory and which are rather accurate since they rely and they use some weather station measurements. But you cannot have this kind of weather forcing all over the planet. So we try to degrade, especially on the precipitation, since it's one of the hardest variable to measure accurately. So we degraded it either by dividing it by 2 or multiplying it by 2. So that's for the weather forcing perturbation. As well, we use the multiphasic version of Crocus, which means that in each of these 120 runs, the description of Crocus was different, either regarding the compaction rate or the metamorphism of the grain, how it's parameterized, or the fresh snow density calculation. There are a bunch of equations which are different in all of these particles of the ensemble. For the observation, we have the snow depth maps that I showed just before. And the initial resolution is at 3 meters. We just aggregated them at 250 meters to be consistent with the model. The assimilation is made with a particle filter, which impact is shown here. So each circle is one of the 120 simulation, and that's the snow depth. Oops, where am I? That you see here. And that's the distribution of the snow depth in the 120 for 1 pixel, sorry, before assimilation. That's our Pleiad observation. We know the error because we calculated it with the ASO product. And then after the particle filter, it's duplicating the particles and you end up with another distribution of the snow depth for this point. So we apply this for each grid point, and then we let the simulation go on. And so yeah, we have, when we don't assimilate, it's the open loop, and then we can use it to evaluate the impact of the assimilation. We as well have 2 ways to evaluate the impact independently, either using snow meltout dates from Sentinel-2 and Landsat 8 images. And again, for the 2018 years, we have another Pleiad acquisition in May, which was not used, which was not assimilated. So it's an independent snow depth measurement. How it looks, the results. So here it's the view of the catchment and the simulation grid. So the color scale is inverse compared to the beginning of this presentation. So now thick snowpack is in white and thin snowpack is in blue, dark blue. On the left, you have the open loop. So without assimilation. In the middle, it's 3 times the same map. It's just the Pleiad observation on that date in 2015. And whoops. And on the right, it's the analysis. It's the snow. It's the model after assimilation. And the first row is when we degraded the precipitation, dividing it by 2. The middle row is when we left the precipitation unchanged, and the bottom one is when we multiply the precipitation by 2. And you can see that the assimilation seems to modify the snowpack state. The right column looks a bit more closer to the middle than the left one. And especially we managed to bring in and to put some spatial variability, which is lacking in the open loop. That's another way to look at the impact of the assimilation. It's just we calculate metrics over all of the area. We just take average of it. And each arrow is for 1 date and 1 experience, precipitation experience. And the beginning of the arrow is in the open loop before assimilation, and the end is after assimilation. And so here you can see that in all experiments and for all dates, the mean spread of the ensemble was reduced, as well as the mean absolute error. So the decrease of the spread means that we managed to reduce the uncertainty of the model, or at least we selected particles so that there's less spread. And the mean absolute error, it's expected as well, since we want to bring the model a bit closer to the observation. So that's the distance to the observation. On the right, same thing, the CRPS, which is a way to measure the difference between a robust way to measure the difference between an ensemble and an observation. We decreased the CRPS, which is a good news, and we increased the correlation for, again, all dates and all experience. And that's for the 2018 years, and the full line is the assimilation date, and the dashed line is the May observation, which is independent. And you can see with all the dashed line that it follows what occurred on the assimilation date. So we still reduced the spread 80 days later in May. We reduced the mean absolute error, we increased the Pearson correlation, and we decreased the CRPS. So that we see that the impact of the assimilation is still holding 80 days later, and that's an independent measurement, which allows us to see that. Now about the snow meltout dates. So that's, we have it for 3 winters due to Sentinel-2 image availability. And here, what it shows, this histogram, is the impact of the assimilation on the snow meltout date estimation. And when you're on the positive side, it means that you improved the snow meltout date simulation with the model. And when you're in the negative, you degraded it. What you can see is that with the reference weather forcing, when we didn't degrade the precipitation, there's barely any noticeable impact of the assimilation. Sometimes, some places we improved the SMOD prediction, sometimes we degraded it. Nothing interesting in average. But there is a positive impact for more degraded forcing. So here, when we divided the precipitation by 2, with improvement of 10 to 20 days in average. Oh, that's the median actually, yeah. And slightly less marked, but still improvement when we increase the precipitation by 2. So again, that's a independent way to estimate the impact of the assimilation, satellite-based as well. So you could imagine reproducing that in any place of the world. But what does it mean to assimilate snow depth in this model? Because the model is not really handling snow depth as a variable. It's handling snow mass and in each of its layer and its density. So here, which means that when you assimilate snow depth in it, you could either modify the density of the model or the snow mass. When we degrade the precipitation, we are degrading the mass. I mean, we are we are degrading the mass which is entering the snowpack. So we expect to correct this at least with the assimilation. And that's what we see on the left. So that's when we divided the precipitation by 2. In the open loop, we see that that's the gray shaded area here. And in the analysis after assimilation, we corrected this precipitation gradient, which means that we selected the members of the model which had more precipitation. So that's what we want. We want to correct an underestimation of the precipitation. But at the same time, we changed the density of the snowpack. And so that's due to the multi-physics of the model. So here it's just 3 different ways to calculate the compaction rate of the snowpack. I can't remember which paper it refers to, but what we need to know is that B92 is compacting slower than T11, which means that in the analysis, you can see that there's slightly more B92 than T11, which means that the snowpack is going to compact slower, and then the snow depth is increasing that way, even with the same precipitation as input. So that's something to be careful with, because even if you want to correct a bias in your precipitation, you could completely correct it with just a multi-physics model. And that was found as well in other studies. So the conclusion from all of that is that we are quite happy with the satellite photogrammetry products. It's a good compromise of accuracy, and it has of accuracy and covered area, and it has the strong advantage that you can acquire data anywhere on Earth. And it should become easier to get these data since there are more and more satellites, stereo satellites, which are launched. The particle filter was quite efficient to do distributed assimilation. And you could use it as well with more acquisition within 1 winter. You can use it in a sequential way, and you can as well do forward prediction, forward simulation, and prediction of the runoff with this method. Yes, there are still many things we didn't do and we didn't answer with this work. So here we only degraded the precipitation, but we might want to apply that to other weather other weather variables, or just directly try with weather forcings which are known to be less accurate than this one. There are some processes which were not represented in this model, such as the wind transport, the complex interaction with the vegetation. There was basically no interaction between grid points. So we know that we can't, that the assimilation is partly compensating for that. That would be interesting to see how we could improve that directly in the model. And we then look as well at the snowpack stability, which is which would give a hint about the avalanche risk, for example. And as well, that's quite a low resolution simulations compared to what was done in the other studies I mentioned. And so it would be interesting to try this at higher resolution, and we assume that it should work as well. What's next? We keep applying this method in many different climate and environment, in the Yezo catchment in the Chile with Thomas Shaw, in the Lotare Pass in the Alps, in Arctic environment. And so there are some problems related to different areas, but we can try to see how much it works in all these places. And what's next? I defend my PhD on Monday, 8th of February. And if you're not scared by French language, you can just attend, since it will be in as a video conference. You can ask me for the link. And I will be starting a postdoc soon somewhere about some topic. So if you have some ideas about that as well, I would be happy to discuss it. Thank you very much. And I noticed, looking at the list of people attending, that I didn't mention the co-author of the cryosphere article, which helped for the first half of this work. So thank you to them as well. That's it for me.
Great, thanks a lot, César. That was great, excellent presentation, right on time. I'm going to use the chat window to get some of the questions started. So I'll just read these in the order they were submitted. So Jessica Lundquist has a question about the Pleiad data. So how frequent are the acquisitions globally, and how difficult and expensive is it to get the Pleiad data?
So they are acquisition on demand. So you must order them in advance, like a few weeks up to a few months before. And you fill a form and you say which area you are interested in, and they will tell you if they can do it and not. And then they try. And if it works, they send you the images. But if it was just cloud covered all the time, if the weather doesn't allow to take images, the order might not succeed. So there is no systematic acquisition. It's really on demand. But the price, I can't tell. I think there's a price per square kilometers. Here we are very lucky. We get them for free because we are a French researcher. And I know it's not a really satisfying answer, but it's yeah, I think it's a few dozens euros per square kilometers, maybe something like that.
Okay, great, thanks. Thomas Shaw asks, would you think the optimal number of scenes to obtain per season is balancing, cost, processing, and uncertainty?
Well, for processing cost, I would say it's not that much here. It can run quite fast, and when you get the images, you can get the snow depth map within a day, I would say, afterwards. So I don't think it's really a limitation. And then regarding the accuracy here, with 80 days difference, we still notice large differences. Yeah, if you think of the random error for a 3 meters pixel at 70 centimeters, sorry, you might want that the snowpack changed by at least that much if you want to notice the change at very high resolution. So yeah, it will depend on places and processes, but one way as well is to just degrade a bit the snow depth map in resolution, and then the error decreases, and then you could use some high frequencies acquisition.
Right. Okay, great. Question from HP was whether there's any calibration performed for the comparison between the Pleiad retrievals and ASO.
Calibration, I'm not sure what's meant with that. So the two snow depth maps were really calculated independently. There's just one step in which we ensure that our elevation, our DEMs are co-registered with the DEMs from ASO. So we just shift our DEMs on the same grid as them. And then that's it. The workflows are just completely independent.
Okay. I have one quick question is that you mentioned on your last slide that these types of missions will be increasing in the future. Can you provide some specifics on the names and when and kind of what the plans are for these types of photogrammetric missions?
Yes, so as far as I know, there are two main commercial companies which are selling these kind of images, which is Airbus and Maxar, which is running the Worldview satellites. So you can buy from them satellites, and they just keep sending them. So they will have there are many projects starting really this year and the coming years. So there should be really lots of offer on this side, but it can be expensive. So yeah, Maxar and Airbus, and then what I know in France, the CNES, which is the CNES is launching a program, CO3D, which should give access to some images to researcher, but it's really not known at which cost and which conditions. So yeah, again, it's not really a super open science field for the moment, but we can hope for improvement in that.
Yeah, great. Thanks. I'll take just one last question from the chat window from Mackenzie. She's asking about your confidence in sort of translating the uncertainty between different basins. So is the basin that you're working with similar in elevation, topography, and vegetation to Tuolumne, for instance?
Yeah, that's a good point. We would still need some more study case to evaluate the accuracy. We have some ways to transfer. So the vegetation is might be a good limit. Like if you have really different vegetation, bushes or herbs, it might just look really different and introduce different gases in your measurements. One thing which we can use is that we have stable terrain, which is like bare rock or really low grass. And that's directly related to your acquisition. And that's an indication of the accuracy of the elevation difference. And then we transfer that as well on the snow depth measurements. So we transfer from a catchment to another one, but as well within the same scene, we can know a bit what's the accuracy of the elevation. And then comparing as well with other studies in glaciology, we can see we get a good impression of what's the accuracy expected, and what the number I said here are totally in the range of what's found in the literature.
Okay, great. Well, thanks a lot, César. Great presentation. Thanks everybody for your questions. So we'll move on in the agenda now. So we will pass the screen sharing to Gabby Schwaizer. So Gabby works for NVO, which is based in Innsbruck, Austria. One of the goals of these Sinter meetings is to not just provide science talks, but also to have updates on projects that are ongoing within the snow community. So one of these emerging projects is called, it's the second phase or next phase of SNOWPEX, which was a project that some of you might be familiar with from a few years ago as a satellite snow product intercomparison. So Gabby is just going to give a 10-minute status update on SNOWPEX Plus, which is just been kicking off the last month or two. So Gabby, I see you have your screen sharing, and take it away. We can't hear you, but we can see your screen.
Sorry.
There
So
we go.
now it should work.
All good.
Thank you very much for the introduction, Chris. It's a pleasure for me to introduce today a project update on the SNOWPEX Plus. And before we dive into the SNOWPEX Plus, and probably not all of you are aware of what SNOWPEX really is. So I'd like to give you a short retrospect on the SNOWPEX activities. The original motivation for this was actually a publication of Chris and in 2012 on the snow cover extent from the NOAA snow chart from the climate data record, which shows the rate of the June snow cover extent from 1979 to 2012, which shows really a decreasing trend of about 21% per decade. And this is now the trend of the June of the minimum northern hemispheric snow extent. And we were wondering, okay, could this be also reproduced by other satellite snow products? And therefore we launched in 2014 within the ESA quality assurance framework for Earth observation, the SNOWPEX project, which is the satellite snow product intercomparison and evaluation exercise. In this project, we had 12 hemispheric and global and 4 continental snow cover extent products participating, plus 7 hemispheric or global snow water equivalent products. These products are not all generated and hosted by the project team, but we were successful in inviting all the different international snow product providers, providing their products, participating actively in the project. Also we organized 2 international satellite snow product intercomparison workshops, the ISPI workshops. So one in July 2014 and one about a year later in Boulder, Colorado. And we had quite an active discussion with the international snow community to elaborate the validation and intercomparison protocols and methods. These are available online, so everybody can access these. And all the participating products were, of course, intercompared and validated with independent snow reference data. So therefore, we used in situ data for both the snow cover extent and the SWE products. And we used high-resolution snow maps from Landsat data mainly to evaluate also the snow cover extent products. Additionally, we had some trend analysis for the period 1999 to 2013 for the snow cover extend products and 1981 to 2010 for the SWE products participating. So just to show you some results from this SNOWPEX activities, here you see the intercomparison results on the left side for the snow cover extend products for the period April, May, June 2006, and on the right side for the SWE product intercomparison. And without going into detail, I just want to show you here, if you look at the colors in the left side in the tables, as more red the upper left, the upper right part is, as bigger differences we have between the different products, and in the lower left part you see the bias between the different products. So as more pink it is, as more positive the bias is, as more bluish it is, as more negative is the bias. And at the very left side you see what comes out if you consider all the valid pixels. That means snow covered and snow free pixels. So here the agreement between the different products is quite good, so around 15% at the maximum. But if we consider only snow pixels, so this is in the middle, then you see that the differences are quite large. And here we have differences up to 35–40%, and this could be even larger, so up to 50%, depending also on the surface class we are looking at and on the season. On the very right side, you see the SWE product in the comparison. Also here you can see quite a big spread of about 2.5 to about 4 times 10 power 15 kilograms. So this is really a huge difference, and it's not consistent at all between the different products. And if we have a look at the trends, so also here it's on the very left side again the trend for the Northern Hemispheric snow cover extend product for April, just next to it for June. And for June we see this decreasing trend for the IMS products, but not at all for most of the other products. So there is quite again a big spread, but the trends we have seen in Dirksen and Brown in 2012 could not be reproduced by the other products in that data set. And also for the snow water equivalent trends, which is on the very right side now in the lower part, you see that here is also quite a big spread between the different products again. So the motivation for SNOWPEX Plus was now that there are in the recent years we had new satellites, new sensors coming up. There were new snow algorithms and products coming up, so including also partly the uncertainty estimation per pixel. It's also that we want to consolidate the trends of the snow extend or the snow cover and the snow water equivalent, and we want to extend the period with the 2015 to 2020 period, because all previous intercomparison validation activities were of course limited to until 2015, and for the intercomparison itself we only selected 5 years from this full range we had, because not all products are available all the time. So the main objectives of the SNOWPEX Plus is of course to perform the validation and intercomparison again for the satellite-based snow cover extend and snow water equivalent products, which are available for continental to global scale. So this is really crucial that we are not talking about local products, but we want to get an information on the global scale ideally and on a daily basis. We want to do that for the period 2015 to 2020 and consider of course new sensors, new algorithms, and if available the product uncertainty. It's also planned to organize a third international satellite snow products intercomparison validation workshop. It's currently planned for the second or the third quarter 2021. It depends a bit on the COVID-19 situation and what is possible in the next month. But this is definitely on our agenda. And of course, we will prepare and deliver all the documentation on the validation and intercomparison activities, as well as on the updated trends, including also the outreach activities to the global climate research community. Further, we want to contribute also to the advancement of the procedures for the snow monitoring from Earth observation data, so from optical satellite data and from passive microwave data. And this is really crucial, and we are not want to rate some of the products, but we just want to have an objective view on, okay, what is available and how are the differences. And last but not least, consolidate, of course, the estimation of the trends in the seasonal snow coverage. This is not just an overview on the global and hemispheric snow cover extent and sweep products we partly already had in the SNOWPEX project, and we hope that these will also participate in the SNOWPEX Plus activities. Some of the products are not active anymore, so we will, of course, not consider these anymore, but might be replaced by newer products or other sensors. Additional products are added, and we are now in contact with the product providers also to be active also in SNOWPEX Plus and help us to find the next snow patterns and the trends in the snow products from satellites. Further, we want to extend, of course, the reference datasets for the period 2015 to 2020. This addresses mainly in situ snow data from synop data, from snow transects, including also snow water equivalent and E-codes if available, so just describing the snow state, including also snow pillars, so from the snow telemetry from, which is, I think, just an American network, and the snow course data and products, and if available, also additional meteorological info, which might help to identify snow-covered areas. Further, we had gridded snow models as reference data and high-resolution optical satellite data, and here we select these usable data sets manually to cover really the full, not only the northern hemisphere this time, but the full globe, plus to cover different snow conditions, different seasons, different surface types, and so on. So you see here just some examples which are our starting point, and from here we extend the reference data set for the next activities. So just the next steps is for us, the main step now is to get the international providers of the daily, global, or hemispheric snow products on board to be active in the SNOWPEX Plus activities and to provide their products that we have a databases to work with. Further, of course, we want to extend the snow reference data. This is really crucial to have here quality controlled in situ snow data sets, so we have to bring everything to a same standard, and only this is quite a bit of an effort to work with some very local data sets which might be excellent, but which are totally out of the limit what we could work with. Then we have, of course, the gridded snow models and also the reference snow map from selected high resolution optical images. Here we definitely want to add also additional algorithms for the generation of the reference snow images, because most of the algorithms which are currently used for generating reference snow maps are based on the NDSI, so on the normalized difference snow index, and this is quite a bit tricky if you validate NDSI-based products on a global scale with NDSI-based reference maps. So this is always, of course, very similar, and the aim is to have here something independent, like, for instance, multispectral unmixing approaches or machine learning approaches, something like that. So something which is really independent. And of course, we have to review and update as needed the methods and the tools for the satellite snow product intercomparison and validation activities for this period. So as my last slide, I just want to inform you that we will have a virtual SNOWPEX Plus information meeting on the 3rd of February from 4 p.m. to 8 p.m. Central European time. So this is 10 a.m. to 2 p.m. The US time. Participation is, of course, free of charge, and registration is online via the snowpex.nvo.at webpage. So it's crucial for us to have all the providers from the satellite snow products on board to be active here and we invited most of them, I think, already personally. And just to announce it here also, we have this SP3 workshop planned for the second or third quarter 2021, but further details on this will follow when we have more ideas on in the next month how the COVID-19 situation will proceed. Thank you very much for your attention, and with that, I stop here.
Great, thanks a lot, Gabby. There's a couple questions in the chat box. One from Ned Baird, focusing on the point that the products work well in some cases in some regions and work less well in other regions. So do you have thoughts on the sort of regional perspective on the intercomparison of some of these products?
Yes. So basically, if we validate the products, I think the typical RMSE was about 15% with a bias of ±8%, but there are higher differences up to 50% RMSE for some classes, like for forested areas or also in steep mountainous terrain. This also depends, of course, on the thematic information you're validating. So either you're validating the snow on the ground, applying a canopy correction, or you validate the viewable snow, so in forested area, the snow on top of the forest canopy. And these are all things which were considered in the intercomparison and validation activities and result in different accuracies compared to the reference data sets. For the SWE products, also here we had an RMSE between 40 and 70 millimeters. So it seems that products including an assimilation of in situ data sets had some better performances in comparison to the products which were only relying on satellite data. But this also needs to be further investigated.
Yeah, great. Thanks, Gabby. And we're a bit tight on time, but Ann Nolan points out here that we could also consider using other snow metrics, including annual frequency of snow in a grid cell and snow disappearance date. So those are good suggestions from Ann. So thanks for that comment, Ann. I think what we'll do is, in the interest of time, we'll move on. So thanks a lot to Gabby for the overview. And again, I encourage people to keep an eye open here for the virtual SNOPEX meeting. And if you have a product that you think would be useful and should be part of SNOPEX Plus, and you haven't been contacted by the team yet, please reach out to Gabby. And I guess that goes for our reference data sets as well. So thanks a lot for that overview, Gabby. Now we'll pass the screen sharing over to Mackenzie, who is going to provide us with an update on a snow science webinar series that the planning for that is underway. So Mackenzie, I will pass it over to you. Thanks.
Great, thanks, Chris. I'll make this quick. So we could not have in-person snow school this year, and our effort to sort of keep that in place for this year was to replace it with a cyber webinar series. And this is sponsored through Kawazi. And it's really focused towards new and continuing students in snow hydrology. So it's really introductory material, and we'll have 5 webinars. They'll be on the last Friday of every month, January through May. And they'll always be at the same time, 1 p.m. Pacific, 4 p.m. Eastern. And let's see. So the first one will be field methods taught by Nick Rudder and Alex Langlois. And if you're interested, I'll let you read through the introductions, but just in the interest of time, I'll keep moving through these. The second one will be snow energy balance, taught by Jessica Lundquist. Sorry. The third one will be taught by myself, and it'll be about remote sensing. I'll cover optical, LiDAR, and photogrammetry. Will also be a hands-on introduction to snow radiative transfer. And then the fourth content topic will be microwave and radar remote sensing, taught by Eli Deeb and Chris. And then the final one, oh, you got the meme instead of the other one. The final one is diversity, equity, and inclusion in snow science and hydrology. And then I gave you a meme just so you can remember that snow school is in the computer this year. And we will resume regular snow school next year in person in Utah.
Great, thanks, Mackenzie. Super helpful overview, and it's an exciting series. We can at least keep things going. Anne asks if they're going to be recorded, and I think that's the plan.
They
Right?
will be recorded and they will be archived with Kawazi.
Right, and do you know what the latency will be between when the webinars happen and when the recordings will be posted? Maybe that's a bit hard to answer right now, but Jennifer,
that would be a question for the Kawazi folks, but I think it's pretty quick after.
Great. Okay, fantastic. So we're almost through the agenda, but actually, Mackenzie, since you have the floor, why don't you keep it? We were hoping to get some quick updates. I know conference attendance is not possible these days, but both the Western Snow Conference and Eastern Snow Conference are still proceeding in other formats. So do you want to, Mackenzie, provide a quick update on the Western Snow Conference? And then I think Eli is going to jump on and talk about ESC.
Definitely. So the Western Snow Conference is virtual this year. It will be April 12th through 15th. And the theme of the Western Snow Conference is bridging the gap between research and operations. And you have until the end of January to get an abstract in for that.
Great. Thanks, Mackenzie. Encourage people to do that. And on the Eastern Snow Conference side, Eli, you're up.
Thanks, Chris. You can hear me okay?
Yep, you're good.
Great. So the 2021 Eastern Snow Conference will be held virtually. It'll be Wednesday, June 9th. We haven't sent out any official information, but I think we've agreed upon that date, Wednesday, June 9th. And the Eastern Snow Conference this year will be focused on student-led research and presentation. So we're really encouraging faculty advisors to encourage their students to present to this. We're going to have solely student-led presentations likely, as well as posters. There'll be special discussion sessions outside of the presentations for SnowX, and we're thinking that there will be no cost for registration. We feel that we have enough funding to cover that for 1 year. There'll also be student awards, and the presentations will be recorded ahead of time with the presenters available for questions afterwards, similar to the way other virtual conferences have been run recently. And then finally, I also want to put a plug in for the Eastern Snow Conference in 2022, because it'll be a unique opportunity. It's going to be in Saskatoon, Canada. The Eastern Snow Conference, for those of you who don't know, oscillates between the United States and Canada. So in 2022, it'll be back in Canada in Saskatoon, and it'll be in conjunction with 2 other meetings, the Canadian Meteorological and Oceanic Society, as well as the Canadian Geophysical Union, and actually 3 meetings, Canadian Society of Agricultural and Forest Meteorology. So there'll be 3 other concurrent meetings. Hopefully by that point, it'll be an in-person meeting. The dates for that are May 29th through June 2nd of 2022. I know it's a long way off, but it might be a good opportunity to gather there. And we'll have specific Eastern Snow Conference sessions held concurrently with the other organizations. So look for some information about this coming summer's virtual conference on CryoList, as well as we can probably distribute through the Sinter email as well, if that works. And feel free to contact me if you have any specific questions.
Great. Thanks a lot, Eli. That sounds like a great format for the ESC this year. And I know there was a joint CMOS CGU Eastern Snow Conference in St. John's, I think around 2007. It was a lot of fun. So it's nice to have something hopefully to look forward to that we can all attend in person in Saskatoon in 2022. So that takes us through the agenda today. Thanks a lot to everybody. Thanks to all the presenters and all of you for joining. So our next meeting will be sometime in probably late March or early April. We haven't scheduled a date yet. We'll get back to you with that. We'll keep you posted on all things Sinter through the email list. And if you have any suggestions for agenda items for the next meeting, please email me directly. And again, it can be a science presentation. It can be a project update, anything of programmatic interest to the snow community. Yeah, so please reach out to me with your agenda suggestions. But I think I'll wrap it up here. Thanks to César and Gabby and Mackenzie and Eli for keeping us well informed today. Everybody, stay healthy, stay relaxed best you can, and hope to see everybody again soon. Nice to see so many familiar names on the attendee list today. Okay, take care. Thanks, everybody. Oh, and thanks to HP for hosting. I should have made that clear. HP keeps this machine running smoothly every quarter. So thanks a lot, HP, and thanks, everybody.
I'll send around a link to the recording as well.
Okay, much appreciated. Thanks, HP.